Hi guys. Hopefully you guys are having a great weekend so far. Um, so I wanted to make this video because I know this unit is quite a bit challenging, or at the very least, it's a little bit different from what you've seen before. So I wanted to do my best to help explain some of the concepts that we have here in number theory. Um, this gonna I think this is gonna be for me at least a two-parter. For this first part, I wanted to focus on Gerber's class a little bit more. And then with the other video that I'll upload soon, I'll focus on meat section a little bit more. So for this first video, we're going to try to explain some of the concepts of Gerber's class, and we'll see where we go from there. So in particular, I want to explain two concepts. There are two concepts here that are very, how shall we say, new, at least to most people, that being modulo and divisibility. Okay, so let's talk about this. So these concepts are pretty challenging, but nothing. I I think once you see a couple of them, it won't be as scary. So for problem three, explaining kind of how problem three works, it's pretty simple in theory. It's you divide A by B and you need to find the remainders. And we can't use a calculator except for individual steps, and we're required to show our work. Okay. Well, spoiler alert, no calculators here. Got no calculators. I got glasses. But that's about it. So I'll show you how I kind of do these. So suppose we have to divide A by B, where A and B are the following. And I'll come up with a number. So we'll say A is equal to, hmm, let's say 12 to the 20th power, and we'll say B is um we'll say B is 7. We'll look at that. Okay. So obviously this is a big number. So obviously this is a very big number divided by 7. And spoiler alert, a regular calculator might not be able to handle 12 to the 20th, which is a little bit of a problem because you kind of need to know what 12 to the 20th is, at least in theory. So the question is, how do how do we find and we're gonna say we have to divide A by B and find the remainder. And we're going to assume A and B are the following. Right. So obviously this is a very big number. 12 to the 20th is a very big number, and we have to divide it by 7. And your calculator might not be able to handle that number. So how do we find the remainder of remainder when we can't even figure out what 12 to the 20th is? And so that's the $1,000,000 question, right? And so what I propose to you guys is, what if we don't even need to calculate 12 to the 20th? What if we can just what if there's kind of get around that fact? Maybe there's another way around the fact of having to just multiply 20 times over and then divide that by 7. And luckily there is. And that's this concept called modulo. Let's introduce a concept called modulo. So if you're a programmer, in particular, someone who has programmed with C or Java, chances are you have run into the percent sign before. You've used this at least in some way, shape, or form when you've done coding. And when we use the percent sign in those respective languages, just typically we're talking about remainder. And so the idea is really that you're just taking a big number mod by some number and you're getting a remainder. So at its core, modulo is all about remainders. Notice, i.e., divide some number, typically an integer, by another number. Again, this is another integer, and focus on the remainder rather than what we call the quotient. So the quotient. So let's kind of work with this. So how does this work? So how does modulo work? Well, let's take a number. Let's take a look at 12. When I divide, so hopefully you guys agree that when we divide 12 by 7, hopefully you agree that 12 divided by 7 is 1, a remainder of 5. Again, this is just doing basic long division, just like how we've been taught in middle school, heck, even elementary school when we had to learn about multiplication and division. So nothing too crazy. So one way we can write this, one way we can write this is as follows. Is that 12 is equal to 1 times 7 plus 5. Because what we're saying is that 12 is equal to 1 multiple of 7, and then the plus 5 is the extra remainder. So notice that it's a plus 5, since 12 and 5 have the same remainders when we divide by 7, we can say the following. We can say that 12 is really congruent to 5 mod 7. So in English, what we're saying is that when the statement above says the following, that when we divide 12 by 7 and when we divide 5 by 7, we get a remainder of 5. Both of them spit out a remainder of 5, which is true, because when we take a look at 5, notice that 5 divided by 7 is 0, because you can't fit a 7 into a 5, right? And in order to make this equation not completely fall apart, because 5 can't equal 0, we're going to have to add 5 to the other side. So what this is saying is that 5 is equal to 0 multiple of 7s plus 5. And notice 12 and 5 have the same remainders, because it's a plus 5 at the end of every equation that we created. And so that's why we're allowed to say that 12 is congruent to 5 mod 7, which is congruent to show. Okay, so now we know that 12, so obviously, so now we've shown that 12 is congruent to 5 mod 7. But modulo has some very unique properties that we can do, that we can use. So we have some very unique properties for modulo. And there's quite a few of them. And I will hunt. Let me see if I can go find it. I'm going to use Mead's, Professor Mead's slides for this one, because he leaves some very good ones. But suffice it to say that when we're talking about modulo, just like how multiplication, division, addition, subtraction have their own properties that they get applied, so too does modulo. And while you do not need to prove this, I will never ask you to prove this. There's quite a few properties that we can use here. Every single one of these bullet points here are properties of modulo that we can use to our advantage, which are very, very useful. And I can explain this another day, but suffice it to so the picture below shows some very interesting properties. I can spell properties of module that may be useful. So these guys here is that now that we know how this works, basically what we're saying when we're talking about module is that A and B have the same remainder when divided by M. We can say quite a few things about this based off that module statement. There's quite a few things here, but the property that I'm most interested in is the final bullet point. That being, if A is congruent to B mod M, then for some natural number K, B to the K has to be congruent to A to the K mod M. Or so in other words, if I know that two numbers are congruent to each other under some modulo, it's basically saying that essentially we can raise both sides to the same power and they will still be congruent, which is actually really, really powerful when we're doing things. Also, quick side note, there are many ways to denote modulo. I believe Gerber's notation is having a subscript on the congruence. So for example, if I wanted to say 12 is congruent to 5 under modulo 7, I could say the following. For this. So we could say that 12 is congruent to subscript 5 mod 7. Nope. This is supposed to be 7, 5. Or we could say that 12 is congruent to 5 under mod 7. So either you can bring the word mod 7, you can put the phrase mod 7 after the 5, or you can put it as a subscript. Either way means the same thing. So both mean the same exact thing. All right, so that's that. But now, in either case, we know, in any case, we know that 12 is congruent to 5 under mod 7. And hopefully you agree that 20, let's take 20. 20 is a natural number because 20 is a whole number that happens to be, well, positive, or an integer that happens to be positive. So it fits the definition of a natural number. Why did I pick 20? Because originally we had to divide 12 to the 28 by 7. And so sometimes it's really hard to work with big numbers. So what we can do is make these numbers smaller. What we're going to do is take our value of A, and try to make him smaller using modulo properties. Well, since we So since we know that 12 is congruent to 5, since we know that 12 is congruent to 5 under mod 7, we know that 28 is a natural number. What we can do is we can use this nice little property here, this final property of modulo, and say the following. We get the following, that essentially 5 to the 20th is congruent to 12 to the 20th under mod 7, which is actually true, because it says here that if 12 is congruent to 5 mod 7 and 20 is greater than or equal to 1, then we know that 5 to the 20th has to be congruent to 12 to the 20th mod 7. And to prove that would require a little bit of a technique that right now might be a little murky. It's called induction. I won't touch that with a 10-inch pole right away, but suffice it to say, there are ways that we can get around it. So for now, we'll kind of accept it a little bit at almost kind of like magic. But now, instead of having to work with 12 to the 20th, I can work with 5 to the 20th instead. If I can divide 5 to the 20th by 7 and find his remainder, that would suffice to show the remainder. Show remainder when 12 to the 20th is divided by 7, because 5 to the 20th has to have the same remainder as 12 to the 20th when divided by 7. So if I can find that remainder for 5 to the 20th, it's the same exact remainder for 12 to the 20th. In other words, I only need to calculate the remainder when I divide 5 to the 20th, by 7, and I should be good to go. I should be good. So we can do that, but, and this is where I'll start to diverge a little bit from Gerber style. Maybe, remember, we're not allowed to use individual calculators aside from individual calculations. Well, this is a little bit awkward because I don't have my calculator. I just have glasses, keys, got my headphones. I got my wallet too, but I unfortunately don't have my calculator at the ready. So I can't, unfortunately, maybe sometimes multiplying by 5 is not easy. And so why do I bring this up? Well, notice that in order for me to go from 12 to 5, essentially I had to subtract 7, because notice 12 minus 7 is 5. Well, who says it has to be positive? Who says that these numbers here have to be positive numbers? They just need to be integers. Well, integers include negative numbers and 0, right? So instead of working with 5, what if I subtract 7 from 5? So when I do that, I find that 5 minus 7 is negative 2. And really what we can say then is that 5 has to be congruent to negative 2 mod 7. And so now you're probably thinking like, okay, that's a little bit crazy to say, James. How can 5 divided by 7 get us a negative remainder? And I'm not really saying that it's getting a negative remainder. I'm saying that, think of it this way. Rather than thinking of it as getting a negative remainder, it's more like saying that 5 divided by 7 gets us the same remainder as if we divide negative 2 by 7 and get a remainder. And you might be thinking, well, how does that work? How does 5 and negative 2 get the same remainder? Well, let's do a little bit of explanation for this. Let's do a little bit of an explanation. Hopefully, you agree that 7 is congruent to 0 mod 7. Or in other words, when I divide divide 7 by 7, and I divide 0 by 7, I get the same remainder, which is, well, 0. And that's true because 7 divided by 7 is 1 with a remainder of 0. 0 divided by 7 is 0 with a remainder of, well, 0. And so we also know that 5 should be congruent to 5 mod 7. This is one of our modular properties. That every integer is congruent to itself under some non-zero mod number. Or in other words, if m is non-zero, then a has to be congruent to a mod m, which is that second property. So we know that 7 is congruent to 0 mod 7, and 5 is congruent to 5 mod 7. Well, what we could say is that since we know that, therefore, it has to be the case that 5 minus 7 is congruent to 5 minus 0 mod 7. And because what I'm doing is I'm taking the left side of both equations, so I'm taking 5, the left-hand side of both equations, so 5 minus 7, and then I'm going to take the right-hand side of both congruencies, which is 5 minus 0, 5 and 0. What I'm using is, again, another one of these properties. If A is congruent to B mod M and C is congruent to D mod M, then that tells me that A minus C has to be congruent to B minus D mod M. Again, this is why those modular properties is actually super, super useful, because it allows us to make those calculations really simple like that. So using these properties of modulo, and if you guys need me to do another explanation of how these properties work, I'd be more than happy to explain that. But for now, we'll just kind of work with this and say that, hey, now we know that 5 minus 7 is congruent to 5 minus 0 mod 7. Simple, doing some math, we get, oh, I don't want to do that. We get that -2 is congruent to 5 mod 7. And using one more property of math or modulos, we get that we can really just switch the numbers around. We can just switch these numbers around and basically say that, hey, since -2 is congruent to 5 mod 7, we can flip the numbers around and we would still get the same truth value. So we can say that 5 is congruent to -2 mod 7, which is what we got here. So that's interesting. We can now go into the negative zone essentially instead, which is really weird and also really kind of cool in a way. So why do I bring this up? So why do I bring this up? Well, I know that 12 to the 20th is congruent to 5 to the 20th mod 7. That was what we proved earlier. Well, since I know that 5 is congruent to -2 mod 7, and 20 is still going to be natural. I don't think 20 has changed since the last time we used them. We can use that final property, that last bullet point that we used earlier, and say that -2 to the 20th, essentially, -2 to the 20th is just the same thing as 5 to the 20th under mod 7. Which really means that instead of 12 to the 20th, 12 to the 20th, I just need to work with -2 to the 20th and divide that number by 7. If I can find his remainder, then I can find the remainder. Then I found my answer. So instead of having to work with powers of 12 or even powers of 5, I'm just going to work with powers of -2. And at least for me, it's a lot easier to work with smaller numbers rather than bigger numbers, even if it's a negative. If it's a negative, we just need to make sure we just need to look out for the even and odd exponents. Odd exponents mean we get a negative number, and even exponents means we get a positive number. But other than that, powers of 2 is way easier than doing powers of 5 or powers of 12. So from a mental math perspective, I cut down my work significantly by just doing these simple properties. So now let's try to find the remainder when we divide -2 raised to the 20th by 7. So let's see if we can find that. Okay, so what we're going to do here is as follows. So we're going to use a concept known as fast modulo exponentiation. Essentially, we're going to break apart the number into smaller exponents that we can work with, and we're going to incorporate modulo behaviors as needed. And here's the demonstration for this. So let's work with -2 to the 20th. Well, again, still got no calculator. I got a Pokeball though, so we'll catch them all eventually. But aside from that, I don't got anything here that would help me calculate this aside from, well, my noggin. So let's hope my noggin remembers how to do this. So maybe I don't remember how to multiply -2 20 times, but what I'm going to use is we're going to use some laws of exponents. Let's use laws of exponents for a second. So using some laws of exponents, what we could say is that -2 to the 20th, instead of having to work with -2 to the 20th, let's just rewrite it in a different way. We could say that this is -2 to the 4th, and then we could raise this quantity here to the 5th power. Because remember, one of the properties of the laws of exponents, at least when we're talking about it, is that when, this is not fun. No, come back here. -2 raised to the 4th, raised to the 5th. There we go. One of the properties of the laws of exponents is that we can essentially take, when we have in order to show multiplication when it comes to exponents, we raise a power to another power. So we're raising -2 to the 4th, and we're raising that to the 5th power because that's the same thing as -2 to the 20th using laws of exponents. Well, doing some math, we know that -2 to the 4th is just really -2 squared times -2 squared. And -2 squared is 4, so it's really 4 times 4, which is 16. So therefore, we have that -2 to the 20th is really the same thing as 16 to the 5th. And you might be wondering, okay, but why does this matter? Well, let's take a look at this. So maybe 16 to the 5th is a big number, right? But we can remember, we can also use modulo properties here. Properties here to help us. And hopefully we're trying to find a remainder when we divide by 7, right? So hopefully you agree that 16 is congruent to 2 mod 7. Because when I divide 16 by 7, I get a remainder of 2. And when I divide 2 by 7, I get a remainder of 2. So 16 has to be congruent to 2 mod 7. Therefore, since 5 is and I can say that 5 is a natural number because 5 is a positive integer. We can say that 16 to the 5th is congruent to 2 to the 5th under mod 7. So wherever I see a 16 to the 5th, I replace that along behaviorally with 2 to the 5th. So instead of saying thus, instead of saying negative 2 to the 20th, which is just 16 to the 5th, I can say that is congruent to 2 to the 5th under mod 7, which is actually really powerful because now I have cut down my work dramatically from going negative 2 to the 20th to just 2 to the 5th, which is a heck of a lot easier when I do this. The only thing I'll note is that notice I didn't say equals, I said congruent. Note that when you're doing these substitutions, you have to substitute in the whole behavior. So we don't want to say that these guys are equal to each other because clearly these two numbers are not equal. What we're trying to get across is that they have the same remainder when divided by some number, or when we're modding by some number, which is mod 7 in this case. So we have this. Now, oops, come back here. Come back here. All right. So now 2 to the 5th, well, 2 to the 5th is just 32, because that's really just 16 times, that's just 2 to the 4th times 2, which is just 16 times 2, and that's 32. By some math. And this, we'll put here, this is by modular properties here. And so thus, we have this with behavior here. And so now, therefore, we can say that negative 2 to the 20th, which was really 16 to the 5th, is just the same thing in mathematically speaking as 32 mod 7. Well, that means if we do 32 divided by 7 is 4 with a remainder of 5. Or no, 4 with a remainder of 4. I can do math because it's 7 times 4 is 28, and 28 plus 4 is 32. So therefore, for negative 2 to the 20th is really just congruent to 4 mod 7. Because 32 is congruent to 4 mod 7, so negative 2 to the 20th is congruent to 4 mod 7. And since negative 2, and we can say since negative 2 to the 20th is congruent to 12 to the 20th under mod 7, that tells us that when we divide 12, when we divide 12 to the 20th by 7, we get a remainder of 4, which is the answer we're looking for. And if we punch that into a calc, if we want to double check, let's go double check and make sure we did it correctly. So this is a website that I use to check my math. So let's punch it in. 12 to the 28 mod 7. It turns out 12 to the 28 mod 7 is 4, which tells me I did do my math correctly. And so that is the answer we're looking for. When we divide 12 to the 28 by 7, we get a remainder of 4. So I hope this helped explain a little bit more of what we're talking about when we're talking about modulo. I will come up with the second video for Gerber's class because I don't want this one to be too long. But I do hope that this video has helped you guys a little bit more. And if you guys have any questions, please feel free to ask me at any point, and I will do my best to help. Take care, you guys, and until next time, I will see you all on the next video. Peace.